Hey guys, welcome to Digital Srini channel on YouTube. And if you haven't already done so, please go ahead and hit the subscribe button because I'm very sure you'll love the content of this channel. Now let's jump on to today's topic, which is coding or putting together a generative adversarial network using our Keras framework. And we are going to focus on CIFAR10 dataset. We are going to train our GAN on CIFAR10 dataset so we can generate some random images from CIFAR10 dataset. CIFAR10, it has 10 classes. I seriously urge you guys to go back one video. If you haven't watched it, please go ahead and watch it because I talked about GAN and conditional GAN at a high level. Well, in fact, we went through the code. And in the next video, we will focus on conditional GAN, like Keras implementation of a conditional GAN. And the one after that, I plan on actually talking about one of the special use cases of conditional GAN, possibly a pix-to-pix, where you convert an image from one modality to a different modality. So for you to be able to be a bit more comfortable in terms of understanding those, it's very important to understand the basics, right? I mean, that's why I'm trying to do this generative adversarial network again, even though I have done a similar video maybe 6 months ago. So I am going through a few slides that I have used in the last video. So if you have already watched it, go ahead and forward this a couple of minutes. But if you haven't, then this is a great place to at least get a good understanding. And then let's jump into the code, at which point it makes even more sense. So first of all, we know why this is a generative adversarial network, because we are generating or faking or creating new data or new images, for example, and then adversarial because our generator is trying to generate this and discriminator is trying to say, this is not a real image, this is a fake image. So we're going to use this competition between generator and discriminator to make each of these better at during our training, and eventually the generator would be at a stage where it learned how to confuse discriminator, let's say 50-50, meaning when you give a real image, it's like, I don't know, there's a 50% chance this is real or fake. Same with the fake images. That's the goal. And networks is basically a neural network that we are putting together and using that to train, to create a competition between our generator and discriminator. And we also, at a high level, looked at it, right? I mean, initially, what goes into your generator? What is the input? The input is some random vector. We'll choose a vector of size 100 filled with some random numbers. That's it. And that goes in, and the generator takes that value, and then it reshapes into whatever the image size that we want it to be. In this case, CIFAR10 dataset has image size 32 by 32 by 3. So we're going to take this and then perform some convolutional operations to get it to a shape that can be resized to 32 by 32 by 3. And our real images are 32 by 32 by 3, and then we supply half real, half fake images during the training of discriminator. Once the discriminator is trained at discriminating, discriminator is just a binary classifier, right? So it's like its goal is to figure out whether it is true or real or fake. Once the discriminator is trained, we are going to keep the discriminator constant, like not training anymore, and then train the generator to get better at faking images, and then supply those updated fake images back to discriminator, and then discriminator gets trained, and this loop continues until n number of epochs. That's at a high level. Let me just skip through this. You can watch my previous video to get an understanding of what are the 5 steps, which I just elaborated in a few seconds ago. Okay, so the training process. Let's look at the code, because this is exactly the same code that we are going to use in a few minutes. So first, let's look at discriminator, because this is the easy part. Discriminator is nothing but a binary classifier, which means it starts with an input image as an input, right? What is a binary classifier? You probably have done this. You have malarial cells or parasitic cells, uninfected cells, right? And you want to train a model that can differentiate these two images. So that's exactly what we're doing here. So you have a convolutional layer, another convolution. That's it. Only 2 convolutions here. This is up to you. This is something I chose to put together. You can just put 128, 64, and 32, and 16, and then flatten it out, and then do other fancy stuff. This is as basic as it gets. So here we have 2 convolution layers, and then we are flattening the output from here, and then we are dropping out 40% of these neurons, and our output is basically 1. Why 1? Because it's a value between 0 to 1. Why is it 0 to 1? Because my activation is sigmoid. Remember, sigmoid goes between 0 to 1. So this is basically a probability. If it is 0, it belongs to one class. If it is 1, it belongs to a different class. So that's what a binary classifier is. And again, we are using binary cross entropy because this is a binary classifier. And we are using a Adam optimizer with the learning rate and the beta factor right there. Okay, and the metrics we are tracking here is accuracy. This is, again, like I said, a simple binary classifier. Now, if you look at a generator, what does it do? It takes in a latent vector as input and it generates an image, meaning my final output must be of size, whatever the size image that I want to generate. In this example, I want my final output to be size 32 by 32 by 3 because that is exactly what my input is going to be to the discriminator. Because what happens? The generator output is going into discriminator along with the real images. So this must match. That's the only thing that you need to take care. Everything that you do in between is up to you, because what goes in? What is the input to generator? A latent vector of size 100 in this example. So first thing first, I need to take that latent vector and then convert that into a size that I can slowly work my way to 32 by 32 by 3. That's exactly why here we define that, okay, first let's start with total number of nodes as 128 by 8 by 8 or 8 by 8 by 128. And then go from 8 by 8 to 16 by 16 to 32 by 32. That's the plan. That's why the total number of nodes here are defined as 8 by 8 by 128. Okay, so once you have a latent vector as input, it's just a vector, right? That means your first layer, it's not convolutional layer, it's not 2D convolutional layer, it's 1D vector. So the first layer is going to be a dense layer, right? With how many number of nodes? With 8 multiplied by 8 multiplied by 128. Whatever that number is, that many number of nodes. Again, why? Because the next step I'm going to do is reshape this dense vector into a shape of 8 by 8 by 128. So what's happening? My input is 100, a vector of size 100, and then that 100 gets reshaped or resized into 8 by 8 by 128. And I'm taking that and reshaping it to 8 by 8 by 128. And now I can apply convolution operations, right? How do we do these in UNIT as part of your decoder? Because we need to upsample it. We need to go from 8 by 8 all the way to 32 by 32. So we use either upsampling or you do conv 2D transpose operation. So in this example, we are doing convolution 2D transpose. And from these many, we are actually going to 128 right there with this kernel size of 4 by 4 and strides of 2 by 2. What happens when you have 4 by 4? Again, you can do the math, or you can just draw a box of that size and then see exactly what the output looks like. So when you have 4 by 4 with a stride of 2 by 2, your 8 by 8 image is going up to 16 by 16. And how many filters are you going to have? 128. And then you do exactly the same operation. Then you get 32 by 32 by 128 right there. And finally, after this, we are going to collapse all of that into 3 channels because our final output is going to be 32 by 32 by 3. And that's what we have. And my activation is tanh, meaning the output is going to be between -1 and 1. Well, we have to think about this. If my output is going to be between -1 and 1, that means my input images, the images that we are going to be using, we need to convert the pixel values to between -1 and 1. Remember how we do the scaling of images? We divide by 255 to bring the values to between 0 and 1. In this case, we have to just convert that to between -1 and 1. Just a quick note before we jump into the code. Okay, this is our generator. Hopefully this is straightforward. Now you may ask a question, why isn't there a compile? If you go back to discriminator, there is a model.compile. Well, we don't have this because we are not training the generator directly. We are training the discriminator directly. Generator is trained via the combined GAN model, which is exactly what we need to define next. So what is the combined GAN model? First of all, a combined generator GAN model has both generator and discriminator in it. Except our discriminator is not going to be trainable. Why? Because we are already training the discriminator somewhere else. And here we just want the discriminator to stay put. And then only so the generator to be trained. That's why we're not training the discriminator, and our model is again we are using sequential method to add the generator and discriminator, and here we are compiling the model. Okay, and finally let's go down one more step. How do we train this? It's pretty straightforward. For ith epoch in number of epochs, meaning we are iterating through epochs. By the way, you cannot just use model.fit in this case because this is a bit more complicated. So you have to enumerate your epochs and batches. That's exactly what we are doing. So for each of these epochs, for each of these batches, well, where do we get batches from? We have to define some batches. So we are going to define a function that actually gives us a batch of real images, a batch of fake images. That's something we have to define, okay? But once we have that, we get our real images and train the model. When you do your discriminator model.train on batch, it's going to update the weights of this discriminator model after training on this small batch, whatever that batch is, 16, let's say. And then we are going to supply fake images, and then we're going to train this batch. And then we have to train the generator. How do we train the generator? We train it using the GAN we just defined. So what does GAN take as input? Well, let's come down here. GAN, my X values for my, we have to generate the latent points, right? We have to generate our vector, and we also define our Y values as 1. By the way, 0 is fake, let's say, 1 is real. And this goes into our discriminator, and our discriminator, we want to fool the discriminator. That's why we are saying, hey, this is a real image. This is not a fake image. So we are trying to fool the discriminator. So finally, our generator or GAN model is trained by training on the batch, and you have your XGAN, which is your latent points, as the input, and your YGAN. So let me go back one step right there. Where are we? Sorry, I was trying to find, yeah, this is the last slide anyway. We'll look at some of these functions once we get into the code, so don't worry about that. So but for now, let's look at the GAN model. We are training on the batch, and this is what we are providing as inputs to our generator. And finally, once this is trained, we are going to save our trained model. Okay, enough. After 10 minutes, we haven't gotten into our code, but this is basically what we will be looking at once I jump into our Spyder IDE. And I am using, again, Anaconda Spyder. It doesn't matter. You can use anything. In fact, let me just go ahead and look at what version TensorFlow and Keras I'm using. So that's all it matters, I guess, at this point. Let's say import TensorFlow STF. And I'm using TensorFlow 2.4.1. And let's do the same for Keras. And I should add these 2 lines as part of my code regularly, but I completely forget to do that. Sorry. Okay, so this is why. Where is it? I can't seem to talk and type at the same time. Okay, there you go. 2.4.3 is my Keras version, in case you guys care about it. Okay, so let's go ahead and go through these again, almost line by line, but let's not waste too much time because we have already checked bulk of the code anyhow. So these are all the libraries that we are going to use in putting together our model. And again, there should be no surprise because we just went through the code where you saw everything. The only thing that you haven't seen as part of the code was like probably this line where we are loading the data for CIFAR10 dataset. And I'm sure, by the way, whatever I'm showing, it definitely works even for MNIST. MNIST datasets, except instead of 32 by 32 by 3, I think MNIST is it 26 by 26 by 1? But whatever the MNIST is, go ahead and put those values there. And if it is an MNIST dataset, then you may have to change a couple of things. First of all, instead of 128 by 8 by 8, this may be 128 by 7 by 7, because that's what it comes down to if you print it out. Let's go through this in a methodical way. I don't want to confuse you. Step back. we just executed, loaded our libraries. Now let's go ahead and load the data. If this is the first time, it's going to take a while to download this entire thing. I have already done this once. So now I have my train X and train Y, test X and test Y. You can do this on your own data. It doesn't matter if you have 10,000 images, of 2-3 different classes. You can go ahead and load that and follow exactly what I'm showing. This is not exclusive to just CIFAR10 dataset. Okay, now as usual, we get paranoid about, in this case, this is a standard dataset, but I always check how things look like. Okay, fine, some random images. And that's a deer. I know deer is part of CIFAR10. Automobile is part of CIFAR10. Horse is part of that. So boat and frog and so on. Okay, so they look okay. The thing I don't like with 32 by 32 by 3 is it's tough to see some of these images here. Even the ones we are going to generate later on probably are going to be a bit worse. So we'll have to squint our eyes to make sure, oh, maybe that looks like a cat or something. Just a heads up. Okay, now let's go ahead and run the next set of these lines. Again, I'm not going to explain this. This is exactly what you have seen in the as part of the presentation. So this is the discriminator, which should be basically a binary classifier. So if you want, let's go ahead and assign a temporary variable to this discriminator and print the model so you can have a quick look of at how this discriminator looks like. So there you go. So we started off with a 32 by 32 by 3 image, and then the first convolution you get 16 by 16 by 128 and so on, all the way down to your binary classifier, right? Just one output right there. Okay, so that's your discriminator. Now let's go ahead and define our generator. Again, we went through this line by line, so let me go ahead and just run these lines and print out the summary. Again, I'm just putting temporary variables there. And if I go back up, the input layer is a 100 size vector. And then immediately when we add our dense layers, how many dense we are using? 128 by 128 by 8. Apparently that means 8,192 nodes, and that's exactly what you have here. Then we are going to reshape that into 8 by 8 by 128, right? And then progressively go all the way up to 32 by 32 by 3. This is our fake image. The output of generator is our fake image, right? So that's our fake image. So once you have that, now let's go ahead and define the GAN. That's generator and discriminator, right? So our GAN discriminator is non-trainable. And let us go ahead and define our GAN. Let's not print this out. And what else do we need? We are almost there. We just need to go ahead and start our training, but we need a couple of functions to provide the training process, to provide the training function with a batch of images. So what images do we want? We want real images, we want fake images, right? And we need to pre-process these images, because if you look at my variable explorer, these images are all array of unsigned integer 8. We want to pre-process them. We want to scale them or normalize them. And I already mentioned the layer that we are going to use. Well, where is my TANH? The activation we are going to use is TANH. So it's going to, my generator is going to provide an image with values between -1 to 1. So we should convert our input images into to a range of -1 to 1. That's exactly what we are doing right there. So this function just changes my unsigned integer 8, 0 to 255 values to -1 to 1. Okay, now what? Now let's let's write a function that generates real samples. What does that mean? Well, it takes basically we have our data set, right? From this data set, it gives us n number of real images. So our data set has 50,000 images. Of those, if my n number of samples is 16, meaning my batch size is 16, it provides me a list of 16 images, and then we are a list of 16 images, and then corresponding labels. Corresponding labels are equal to 1, because these are real images. Real images equal to 1, fake images equals to 0, unless we are trying to fake the discriminator, and then we say, hey, this is a real image, but then it's a fake image. I'm sure I'm confusing you, but think about it for a second. Okay, let's go ahead and run this function that gives us a batch of real samples. And then we need another function that gives us the vector of 100 size, right? Or whatever the size that we define. Why? Because that goes in as an input to our generator. So let's go ahead and take care of that. So here is the function that generates latent points, and we just need to say what is the latent dimension. In our example, it's going to be 100. And how many of these do you want? If our batch size is 16, maybe I should change the number of samples to batch size. If our batch size is 16, we need 16 of these. So that's what this is doing. It's generating random number. And gives us that many samples. So let's go ahead and run this. And now this latent points, this is going to be our input to generate fake samples. How do we generate fake samples? Well, that's what we have generator for. Our generator takes in this latent vector and gives us a fake image. So that's what we are defining down here. Now this fetches fake images to us. In fact, I should basically say fetch fake image or something for this function. But the input to this function is the generator or latent dimension and number of samples, right? Because latent dimension and number of samples are going to be the input to our generate latent points. And once the latent points are generated, we are going to convert those latent points into a fake image using our generator. And then we are going to return our x and y. And by the way, here we are just supplying these as zeros because these are fake images. Here, these are real images. That's why we are labeling them as 1. Here, these are fake images, so we are labeling them as 0. So let's go ahead and run these lines and go down to the training part. So our training part takes our generator model, discriminator model, the GAN model, and our data set and latent dimension, how many epochs you would like to do this, and what is the batch size. You can do 16 batch size, 32, it's up to you. Now, first thing first, let's actually define our batch per epoch, which is the total number of images divided by the batch size. This is something we always do. And of that, I'm only taking half batch. Of this total batch size, I'm only taking a half batch. If my batch size is 16, I'm just taking 8. Why? Because I want to generate half batch of real images and half batch of fake images. Combined, that's one batch of images that I'm using to train the discriminator. So let's go down one step. Again, we went through this exact code a few minutes ago, so let me be a bit fast here. So for each of these epochs, for each of these batches, first of all, generate my real images and real labels. Okay? And how do we do that? We have a function for that, right? Generate real samples. That's exactly what it's doing up here. Generate real samples. It looks at the data set and then it generates that many 16, let's say, batch number of real samples. What do we do? And by the way, the batch size is half the batch. That's exactly why we define half batch up there. So once you have this, now we need to update the weights or train our discriminator model. D model is our discriminator model. G model is our generator model. GAN is our GAN model. Just to make sure you guys understand that. Okay, so now we need to, we don't really need our loss right there. If you want, you can capture that in a variable, but the most important point is you take your discriminator model, update the weights by training it on the batch of real samples with real labels. Good? Now, let's go down to the next step. Once it's done on the real, now let's take the same discriminator model and train it on fake images and fake data. Now we are actually telling this that, hey, this is a fake image and this is a fake label. So this label here is going to be 0. Remember our y fake, if we can see. I can't even find it. Where is my y? Oh, right there. So this one. It is 0. So here, my discriminator correctly knows that this is a fake image, and the discriminator correctly knows that this is a real image and updates the weights. After that, discriminator training is done. Now I need to train the generator. And how do we train the generator? Via our GAN. So that's what we are trying to do down here. So first of all, we need to provide an input to the GAN, which is just generate the latent points, which gives us whatever the batch size is, that many latent vectors, some random numbers. And then my y for the GAN is 1, because we are trying to fool our discriminator that these are real images. Okay, so that's our y GAN right there. These are the inputs to my GAN model. So we're going to train on these two, and then we get our generator loss. We do not really, again, care about these losses. The only reason why I'm assigning them to some sort of to a variable is, as the model is being trained, I just want to have a look at these losses, because eventually what we care about is this GAN model, and that's exactly what we, where is my G model? That's exactly what we are trying to save right there. Okay. I think this is let me go ahead and see if there is anything else here that needs to be. Yeah, I think we covered pretty much every part right there, and now it's time to implement to run this. So first of all, let's do our latent dimension equals to 100. Again, this is the vector that the size of the vector, and I'm assigning a variable for my discriminator and another one for my generator. And my GAN model is a defined GAN, generator, and discriminator. And our data set is basically load real samples, right? I mean, that's what our data set is going to be. And let's have a quick look at our data set size. It's 50,000 by 32 by 32 by 3. So we have 50,000 images. Each is 32 by 32 by 3. And if you look at the values here, they're array of float 32, and they should be between -1 and 1. Okay, now we are all set. Let's go ahead and run the train model. What does the train take? It takes generator, discriminator, GAN, dataset, latent dimension, and number of epochs. Let's just make this 2 epochs. I did train it for 250 and then saved it, but I just wanted to make sure you see something on the screen. Train, okay, apparently we did not run this function. So let us go ahead and come all the way down here. And let's see it train for a couple of minutes. Obviously, you need to have a GPU for training. If you don't have one, use Google Colab. But I'm not a big fan of, I mean, it gives you free GPU, but then it kind of shuts you down after, like, I guess 90 minutes of inactivity or something. So you constantly need to move your mouse. And yeah, there you go. So for each of these epochs, and this is my batch 128, 129 out of total 390. This is my discriminator loss. That's my discriminator loss on real data, discriminator real images, discriminator loss on fake images, and my generator loss. Something is happening, and hopefully it gets better. Not in one epoch, but as you go. So I have done this for 250 epochs and already saved the model. So let's go down and generate some fake images. So first thing first, let us run these 2 lines here. All I'm doing is loading a model. And let's also run this function that shows the plot. This is basically how many ever images that we generate. It's putting that in a grid format and plotting it. That's pretty much it. Okay, so I define my model as load this model. We have already trained it, and I'm just loading it. And generate latent points. How many latent points do we want to generate? For now, obviously the size of the vector is 100. By the way, generate latent points, I'm just calling the function that we already have up here. That's pretty much it. If you see that one, it takes in the dimension and also how many do you want to generate. So for now, let's generate 25 of these, so we can plot a 25 by 25 grid of generated images. So let's do that. And now, how do you predict? It's basically my model.predict. What does it take in? It takes the latent points as the input. So let's go ahead and do that. So I have my X here of size 25 images, each image 32 by 32 by 3. But the values in these images, the pixel values, if you want to call them, are between -1 to 1. So let's get them back to 0 to 255. So let's go ahead and scale them. and let's convert them into 0 to 255 right there. This is all optional. I'm doing that in case you want to save that image as JPEG or something. So let's go ahead and plot them with a grid of 5 by 5. So let's go to plots, and there you go. These are the images, some of the generated images. And again, it's tough. If you squint, they may look like something. Again, that's because these are 32 by 32 images, and maybe I can use a bit more training or play with the discriminator and generator architectures. In a couple of videos from now, we are going to use a unit as a generator. So you can actually take, for example, a semantic segmented image as input and then generate a realistic looking image. So there we may see something a bit more discernible, but this is not bad. I mean, let's go ahead and generate new set of latent points and more images. So some of these now the question is what images? I mean, it's just sampling in the latent space, and it's just plotting some of these, and we don't know where it is sampling. So in the next video, I'm going to talk about conditional GAN, where we can provide a class label as one of the inputs and only generate images belonging to that specific class. So stay tuned for that next video, and please do not forget to like this video if you really happen to like it. If you don't like this video, please leave a comment telling me why you don't like it so I can improve. Don't just hit the thumbs down, because that doesn't tell me why you hate this video, because I want to make sure I generate better content for you guys. Thank you guys again.